Okay, thank you for the introduction. So first I'd like to show you two videos of ambient occlusion. So you can see here on the bottom left. So the goal of ambient occlusion is to darken corners and creases. So in this case, if we look at the pillar in the background, you can see that this shadow is produced by ambient occlusion. However, if you look more closely, you can see that this sometimes disappears. And this is because the algorithm to compute this ambient occlusion is a screen space algorithm. And in particular, if other information is in front of it and it includes the relevant parts, which is in this case the statue, the shadow might disappear. So what we are working on is a technique that uses a ray trace stochastic depth map to resolve those issues. And this is what you can see on the right side. So as you can see, the shadow will no longer disappear in this version, but it also takes a little time longer to render. So first of all, there's a long list of ambient occlusion techniques. So the most popular is probably horizon-based ambient occlusion. There's also volumetric ambient obscurance and scalable ambient occlusion. And for this talk, I'll mainly explain it with volumetric obscurance. However, in theory, you can use any of these techniques. So let me first explain a little bit how volumetric obscurance works and why these shadows disappear. So if we want to calculate ambient occlusion for a point, so let's say it's this point P in the scene, and the camera would be looking from above, we would be interested in how much of this area inside this hemisphere in blue is occluded. So in this case, it would be like 50% free and 50% occluded, which would result in a gray ambient occlusion value. So how do we calculate this in real time? We usually take a couple of samples down from this sampling disk below. So for example, for sample 1, we would do a depth map lookup right here. And based on this, we could estimate how much of the line from this area where we intersect the sampling hemisphere down to the bottom is occluded. So in this case, it would be 50%. So this sample would get a 50% ambient occlusion value. And we could repeat this for multiple samples. Usually we do this for 8 samples. However, if we now pick this sample, sample 1, we also read the depth buffer again at this point. And then we could estimate, okay, this is completely occluded. But the problem is that the information from the depth buffer is not really reliable because we could also have this case right here, but we can't differentiate this from the depth buffer value alone. So here's the video again. So now you know why the shadow disappears. And here's another example where this happens. So if you look right above of these stacks of cards, you will see a shadow down here from the window frame. And this one will also disappear. And here's an example where it's actually not enough to just store the next depth value, since the stack of cards has multiple depth layers. So this is more complicated, actually. One way to resolve this was presented 3 years ago with stochastic depth ambient occlusion. So the idea is that in addition to the normal depth map, which we use to calculate the ambient occlusion, we also create something called a stochastic depth map. So the idea is pretty similar to a depth map. This also stores per pixel depths, but as opposed to a normal depth map, it does not store the next depth value. It stores a random depth value of a random depth layer. And since one random value is usually not very reliable, it stores, in this case, up to 4 random depth values per pixel. So we have some values to work with. So in the end, it would work like the following. If we go back to our sample 1 again, we sample from the depth map. We see, okay, it's outside of our ambient occlusion radius. So then we take a look up in the stochastic depth map, and we can potentially see this depth sample and this depth sample. And from this, we can just say, okay, this depth sample looks good enough. It's in our sampling hemisphere. So we compute ambient occlusion with this. And in that case, the shadow wouldn't disappear anymore. However, one problem is that creating such a stochastic depth map, which is really resource intensive, it requires a lot of bandwidth. So 2 years ago at this conference, I also presented a way to optimize this. So we start again with the depth map. From the depth map, we calculate the ambient occlusion as usual with all the arrows. So you can maybe see that there's a shadow missing here. However, during the calculation of the ambient occlusion, we also remember which pixels had problem when they computed the AO mask. So which pixels are potentially missing the shadows. And in the second mask, we remember from where we need more depth values. So the second mask, this SD mask, pinpoints basically all the occluders where we want to see through. So after we created this mask, we can create the stochastic depth map only for this area. This saves a lot of bandwidth already. And in a final pass, we can then recompute the ambient occlusion value for all the pixels that had missing depth values. So from this on, I now want to introduce our novel contribution, which is the ray trace stochastic depth map. The previous one was done with the rasterizer. And with the ray trace stochastic depth map, we can actually save a lot more time by doing specific tricks. So let's start with a very naive approach. So first of all, let's look at this scene where we just trace a ray for every pixel. And for each ray, we would then intersect the geometry at multiple positions. And now we just need to a random subset of these random positions saved in our stochastic depth map, and we can use this by utilizing the AnyHead shader. So on the right, we would have a ray payload where we save n depth values per pixel, and also a count which remembers how many depth values we have already encountered. And then we use a very old technique, reservoir sampling, to basically store all these depth values in a random fashion, so that we first collect the first n distinct depth values, and after that we each time replace one depth value which we have stored with a new depth value, if necessary. So, however, that's like a lot of rays and a lot of long rays. So we could reduce the length of the rays already by omitting the primary depth intersection. So we already have this in the depth map, so we no need to trace this again. So we can just start the rays at a later point. And we can also use the optimization from our previous paper where we tailor the stochastic depth map basically for ambient occlusion only. So in this case, we would look at each pixel again and check if a ray for this area would actually be required if we compute ambient occlusion. So in this case, we can omit all these pixels on the left because there's no ambient occlusion pixel that would need those depth values anyway, so they are useless. And we save the relevant ones. So now comes a novel contribution. So I will go back again to here. So as you can see, the rays are still relatively long for those pixels. And these 3 depth values on top here are not even needed because we only need this array, this depth value to compute the ambient occlusion. So what we can do is during the first ambient occlusion pass, we can just write these starts of the intervals where we want to start the ray and where we want to end the ray into a separate texture. And in case there are multiple overlapping instances, we just use atomic operations, so an atomic min and an atomic max operation, to store these intervals in a reliable way. What we can also do is, previously we worked with a full resolution depth map and a full resolution stochastic depth map. And it's, I would really recommend working with a full resolution depth map, otherwise you will get major aliasing issues. However, for the secondary depth values, which are only a fraction of the depth values that are being used, it's actually sufficient if we create this in a quarter resolution. And with a quarter resolution, I don't mean a quarter the number of pixels, I actually mean a quarter in width and quarter in height, which means it's 16 times less rays than before. So here's some results if we use a lower resolution stochastic depth map. First of all, on the left, we have a bench in the park. When when we just use a single depth buffer, and you can see the benches glowing on the corners, on the silhouette, because they are missing depth values of the grass on the background. On the right side, you see the full resolution stochastic depth map. In this case, you shouldn't see any more artifacts. And in between, we have the quarter resolution and the half resolution stochastic depth map. And I would say that there's not really much of a noticeable difference between those images. However, the rendering time, which is here, it gets significantly faster. So from 1 millisecond in full resolution to 0.6 milliseconds in quarter resolution. This is for the full ambient occlusion path, not for the stochastic depth map. So there's one issue though with the reduced resolution. So again, we have the single depth version on the left side and the full resolution version on the right side. However, if you now inspect the quarter resolution, you should see, if you look at those pillars, that they flicker a lot. So this is due to the reduced resolution. And what happens sometimes is that a relevant or a row of relevant depth samples just gets discarded from one frame to the next due to the low resolution. However, we can use a very simple trick to ensure that this doesn't happen. So on the left side, you see a 4x4 pixel quad. So each black box is a pixel. And instead of tracing the rays through the centers of each pixel, we can just offset the ray locations to a random position inside this box. So in this case, the blue dots show where we trace the rays. So in the first pixel, instead of shooting the ray through the center of the pixel, we shoot it to the top left of the pixel. And this will then result in this third column, which I called quarter resolution plus jitter. And I think you should not see any that noticeable flicker anymore, and it's quite acceptable. Okay, so another very simple trick is that these disappearing shadows or halos around objects are only noticeable in objects that are close to the viewer. So the further the objects are in the background, the less noticeable they are. Therefore, we can just say, okay, if the object is too far in the background, we also don't need any additional depth values. So this is a very positive side effect. So here on the bottom right, we have an image from the Emerald Square, which is a park with a lot of grass and trees. And before doing this radius cutoff, the rays that we need to shoot are quite long. So this is indicated by this heat map here. So as you can see, a brighter color is a longer ray. However, after using the radius cutoff, we can reduce the length of the rays we need to shoot drastically. Then there's another last problem for screen space techniques, which is the problem if we want to sample near screen borders, since they are usually screen space. So please pay attention to this shadow here on the right in the on this slab. So as you could see, it just disappears, and I think it's quite noticeable. Oops. Okay, so and this is so what we came up is we could just increase the size of our stochastic depth map by a certain portion. So you can see in the screen box, this is what the stochastic depth map usually covers. And this one is the extended guard band, which we now only have in the stochastic depth map, which is then also in the reduced resolution. And this is, as you can see on the times, it is quite fast. So previously it was 0.48 milliseconds on this scene, and now it's 0.53 milliseconds, even though there's a larger portion of rays that needs to be traced. But the positive side is that these rays are relatively small, so it's fast. So let's go to the performance evaluation. So we did this for our most difficult scene, which is the Emerald Square with 10 million triangles. You can see a small snippet of the scene on the bottom right. So again, we see a lot of grass, we see some bushes, and we see tree leaves. And this is notoriously difficult for a ray tracer because of all these alpha tests. So what you might notice, if we take our previous ray traced approach from 2 years ago, it has a really high performance drop right here at 11 seconds because of all this alpha tested geometry. And it's also very variable in terms of performance throughout the scene. Then we have the rasterized stochastic depth map. So this is the previous version of the stochastic depth map, which is overall a little bit more even in terms of performance, but still not great. And then we have the ray traced stochastic depth map in full resolution. So this is already better than the previous approaches. But if we now go to the quarter resolution, which produces basically the same kind of quality, we can see that we are able to consistently stay below 1 millisecond. At last, I want to mention that even though this was with volumetric ambient occlusion, it also works with horizon-based ambient occlusion, which we tested, and should work in theory with all the other screen space ambient occlusion techniques if they are adjusted accordingly. So to summarize, we introduced several optimizations for the stochastic depth map. The first one was the ray intervals, which shortened the rays, thus increasing performance. The next one was the quarter resolution, which further reduces the number of rays we need to trace. The radius cutoff, which discards elements that are too far in the background, then further shortens the rays again. And the lazy guard band also gets rid of the last very common screen space artifact near the screen borders. So thank you for listening, and please feel free to ask questions.
Question from the audience? Here. So, yeah, for work, like, it seems like the experience you are in a university. The question is, have you tried things with like terrain? I was wondering, like, if you can use these techniques in a efficient way for terrain shadowing in mountains. So you represented like a high map.
Yeah, I haven't tried it, but I don't see why it shouldn't work. So I think it should work actually really well because also it has no alpha tested geometry.
What about if it's a cave or something like that? It's not only high map. I think your method should work in that case very well.
Yeah, I think so too.
Hi. If I could understand correctly, this ray tracing is a pre-step before rendering, right?
It's actually in between. So it's the first ambient occlusion mask in which we write out the required information to make the ray tracing faster. So it's like the ray intervals. Where do we need to start ray tracing? Where do we need to end the ray? Then we do the ray tracing, and then we do ambient occlusion again.
So basically, the shading is happening, the lighting. You already have this
I start only with the normal depth map, so I assume that you have maybe some kind of rasterization process before, but you start with the single depth map.
Yes. Thank you.
We have some question. So you were showing this example with the cards, the many layers of cardboard
Yes.
in the foreground. I was wondering, like, if there are really a lot of them, isn't there a risk that you will never sample the data that is
I'm glad that you asked. With my technique, actually not anymore because of the ray intervals. Since, well, in this case, it's this case, right?
Yeah.
So in this case, the background would dictate where the ray should start, and this should be like a couple of centimeters in front of the window. And as you can see, the stack of cards is quite far away from the window frame. So simply due to the ray interval, this issue will not happen. And you can also technically use this to improve the rasterized version of the stochastic depth map. But in this case, it will, so for the rasterizer, this will only improve the quality of the resulting samples and not the time.
Any further questions? All right, then we can conclude the last session of the EGSR.